Hello everyone. Today we're looking at the problem choose k elements with the maximum sum, which was question 2 in a weekly contest for 40. So the question reads that we're given two integer arrays, nums1 and nums2, both of the same length, and we're also given a positive integer k. What we want to do is for each element in the array, we want to find all of the indices j where in nums1 j is less than nums1 of I. This is a bit confusing, so I'll go over it in the example. Then what we want to do is we want to choose the k values of nums2j at those indices to maximize the total sum. And we want to return an array answer of size n, where answer I represents the result for each corresponding index. This is a pretty convoluted and confusing description, but let's go into the example and I think it will make more sense. So given the example 42153 as nums1, nums2 being 10, 20, 30, 40, 50, and a k of 2, this will be our output. And let's actually see how we get this. So what we're going to do is for I equals 0, this 4 here, we want to find all of the indices of nums1 where the element is smaller than this element, right? So this first element is 4. We want to find all the indices where the value is smaller. So that would be 1, 2, and 4. And out of those elements, the ones that will give us the maximum score from value 2 have the values 50 and 30, right? So let's say that again. What we're doing is we're taking an element, finding all the other indices where the value is less, and then for those same indices in nums2, picking the maximum value out of k of those elements that we can. So a bit confusing, but that's essentially what we're trying to do in this problem. If we do that for each, we're going to get 80 because we're going to get 50 and 30 from those two indices. For 2, the only indice that's less is 1, so we can just use this one value of 30 here. For I equals 2, there are no other indices where the value is less than this, so we just put 0 here. For 5, all of the other indices in nums1 are less, so we could pick the two maximum, which would be 50 and 30, giving us 80. Then for 3, we have two indices that are less, so this 2 and this 1, so we could pick that 20 and 30 there, which gives us 50, and that is how we get to this answer. So how do we actually do this? Well, the first thing you might think is to do something brute force. So let's say that we're at this 4, right? How do we find all of the elements that are less than this? Well, we would just have to iterate through the array, right? So we would check 2, see that it's less, check 1, see that it's less, check 5, it's not less, so we can't consider this one, and then we can go to 3, see that it's less. So then we found these 3 indices, right? And now what we need to do is look at these values, and we need to compare and see what can get us the maximum. Then we'd move on to 2 and do the same thing. Well, we could, for example, go to 4, see that it's greater, so we can't use it. We can use this 1. We can't use this. We can't use this, right? So you'll see that really for each element, what we'd have to do is go to every other element in this nums1 array. So that's already O of n squared, right? And then once we actually identify the elements, we then would have to go through all these elements of nums2 and try to figure out which is the maximum out of those, right? So that, again, is going to add even more onto our time complexity. So doing it this way is not going to work. So let's think of a different way that we can approach this problem. So what if we were to sort these two arrays? So let's see what that would look like. So what I've done here is just sort these two arrays. So I sorted nums1 just in ascending order. But notice I've also sorted nums2 relative to nums1, right? So you'll see here that in our original question, 1 and 30 are at the same index. So I want to make sure that when I sort, these will be at the same index as each other still. So really what I've done is sorted nums1, but carried those values from nums2 over to make sure that they still align with the same index. I've also just tracked the original indices that these numbers came from up here, which will be helpful while we're analyzing this problem. So why did we actually do this sorting? How does this help us? Well, remember that the point of this problem is that for each index here, we need to find all the other values that are less than it. And we notice that doing this, was adding a lot of time complexity and would take way too long. But if we sorted here already, we know that if we're at an element, let's say 3, everything that we've seen before it, we know will be less than it. So really, by sorting, what we're saying is that when we get to a point, we know that everything that we've seen before is a valid index. So we don't have to go searching. We know that whatever we've already seen will be something that we can contribute towards our sum. So for example, if we're at 1, we haven't seen anything yet. So really nothing we can do here. But if we're at 2, we could say, well, I've seen 1 previously with a value of 30, so I could use that as part of my sum. If I'm at 3, I can say, previously I've seen 2 and 1, I can use those to contribute to my sum, and so on and so forth. So really, we are sorting so that we don't have to do this searching step. So we've solved one problem, but you might still be thinking, say we're at 5, right? Well, we still now have to go back to this entire array and find the 2 largest ones, right? Because if we want the largest ones to maximize our sum, but how can we do this efficiently? We'd have to kind of go through, kind of look at all these values, compare them against each other. So you could do this in like an O of n squared kind of way, but we're going to do this with a heap. And what a heap will let us do is keep track of only the k largest elements that we've seen so far, so we know that we're always using the maximum ones. And you'll see how this works. So here we're going to start at 1. At this point, there's really nothing that we can do here. We know that basically we haven't seen anything. There's nothing that we can use to maximize our sum. So here it's just going to be 0. So at index 2 here, I'm just going to put a 0 for my initial answer. However, now we need to actually keep track of this in our heap. And what we're going to do is use a min heap. So we're going to push this first element, this value, into our heap. So now what we're going to do is we're going to move on to the next element. So now we're here. So what we can do now is instead of searching everything, all the other indices to see what's smaller, I know that whatever I've seen is going to be smaller already. And I also know that I will have what's smaller in my heap. So here, my heap just consists of this one node 30. So what I'm going to do is just use that as my answer for spot 1. What I'm also going to do is push this into my heap. And since this is a min heap, this will float up to the top and my 30 will now be under it. So now we go to the next element. So here we'll see that we are at 3. We don't have to search. We know that we've already seen smaller things. So here at this point, what we can do is just take what's in our heap. We have 50 total, so we could put that in our last spot here at index 4. So here's where things get interesting. We now want to add this 50 into our heap, right? But we know that our k is 2. We only care about the 2 maximum elements, but you'll see that we actually have 3 elements here. So this is kind of a cool trick to keep track of only k number of elements. So we're using a min heap here. So this means that the smallest element will always be at the top. So if our heap ever becomes greater than k, we can pop off this smallest element. And basically what that's doing is saying, I have 3 elements, but I only actually want to have 2. So let me just get rid of the smallest one. And I can do that very easily with a heap. So what will happen is my heap will now transform. So essentially what I've done with my heap is that I've popped off that 20. So my 30 now takes the top of the heap since it's now the smallest element in my min heap. And I also have this 50 here. So basically what I've done is I've taken 3 elements, I've removed the smallest one, and now I've ensured that I only have the 2 largest that I've seen so far. So now we move on to this spot. So here what we could do is we could take the value of our heap. So we currently have 80 in our heap, and we could put this at element 0. So I'll put that right here. And again, I'm going to push this 10 into my heap. So what will happen is I'll push in this 10, and this will bubble up to here. So this will become my 10, and my 30 comes down here. But again, now my heap is larger than k, so I want to pop this element off. So then what happens is I remove that 10 since it's the smallest element and we want to try to maximize our values. So again, we just have this 30 and 50 heap. Then finally, we come to our last spot. And here we do the same thing. We just take the value in our heap currently and we add it into our slot here. So again, it's 80 right here for index 3. So again, we would add this in 40. We'd end up popping this off and moving that up. But at this point, we finished the question, so there's nothing really left to do. So this will be our answer. So basically what we're doing is we're going to sort to take advantage of the fact that if we sort, we know that everything we've seen is something valid that we can use. But then we're also going to use this heap to keep track of only the k maximum elements so that we always know the maximum at any point. One thing that we have to consider in this case is a little edge case where we have duplicate values in our nums1. So we didn't see this in the previous example, but it's something that we definitely need to consider. Let's think what happens here. So let's have our answer array. It'll be 4 elements. So first thing we do is we'll just say, okay, well, there's nothing I could do yet. So I'll just put 0 at my index 0 here. So now I move on to 2. So at this point, I would have added 3 into my heap. So what should I put in this next spot? Should I put 3? Well, actually, no, I should not, right? Because I only want to consider elements that have value less than me, right? So if I'm at this 2, then this 2, I actually can't use this value here because this is not less than where I am. I can only use values that are less than myself. So what can I do in this case? Well, I could try to go back and see which values are less, and then I could maybe try to update my heap in some way, but that's way too complicated and takes too much time. Really what I can do is I can just store these answers, right? So I saw here for value 2, my answer was 0. So I'm just going to store that in a dictionary. And why can I do this? Well, because if I found the answer for this once, that's not going to change, right? Since this is sorted, if I get to 2 again, it has to be right next to the previous 2 that I saw. So essentially, if I saw this previously, even though I added this value, I know I haven't seen any values that are less, right? Because if I had this 2, there's nothing less than me. If I come here, there's nothing less than me. If I come here, nothing less than me. So really, just by the nature of having this sorted, if we see a value and then we see a value again, we can just reuse whatever we saw. We don't have to do this heap logic. This is kind of an edge case we have to consider where we just take values we previously computed and use those for our answer. And you'll see how this works in the code. So the first thing we do is we want to get our nums arrays sorted in the proper order. So what I'm doing here is I'm just kind of combining all of these. So I'm iterating through the length of nums1. I'm getting nums1 of I, nums2 of I, and I. So really what I have is basically all of these elements together along with the original index that they were at. Then I'm going to sort that, and it'll be sorted by nums1. So here's kind of where I set up the rest of the problem. So I'm going to have my heap. I'm going to keep my current sum. So you could iterate through the heap every time and try to get the sum, but really it's easier to just keep a variable here so that we can reference it in constant time. This is going to be my answer array, and this is that seen values. And this is for if I see repeated occurrences of the same element in nums1, I can just reference that instead of recalculating anything. So basically what I'm going to do is I'm going to iterate through all the elements in my sorted array. So I'm going to get the value of nums1, value of nums2, and the index. So if I've already seen this value, I'm just going to grab it from my hash map here and add it into the answer. Otherwise, what I'm going to do is take whatever my current sum is and put that as the answer. And then what I do is I'm going to add into my hash map that the value that I saw for this nums1 element is equal to my current sum. And this will be a value that I can reuse later on. Now what I do is I'm going to push this new value of nums2 into my heap. And I'm going to add that value onto my current sum. And this is the area where I actually am going to make sure that my heap does not exceed a certain size. So while my heap is greater than k, when I have more elements than k, what I'm going to do is pop off that smallest element and subtract that from my sum. So this ensures that in my heap, I always have the maximum k elements, and that I'm also keeping my sum in line with whatever is in that heap. Then at the end, I just return my answer. So let's submit and make sure that it works. And it does work. Hope this is helpful and made sense. If you liked the video, please like and subscribe, and thank you for watching.